he's going to tell us how Higgs and Higgs phases can be SPT, right?
Yeah.
Something like that.
Yeah.
Okay.
Great. So you can well like this. So everyone, let me start by thanking the organizers. It's been a really fun workshop so far. Sadly, I'll already have to fly out tomorrow. Cancellation stuff, flight cancellation stuff. But I'll be around the rest of the day as well, so looking forward for more fun chats. Okay, let me jump in. As Tim was saying, I actually did change a day or two ago what I was going to talk about, because I thought maybe this topic would be a good fit for the kind of broad audience here. I think maybe this might have a large intersection area with the interest of people. So what I'm talking about today is largely contained in these two works that came out this past year with this lovely bunch of people. So Ryan Thorngren, Umberto Borla, Sergei Moros, Tibor Rakowski, and Ashwin Vishwanath. And so the motivating question that guided our work is basically asking, what really is the Higgs phase of a gauge theory? Okay, and it's also a personal topic for me in the sense that it grew in large part of some frustration that I had also when I was a student. Maybe like many of us, right, when you get your first course in QFT, like in my case, we used Peskin's book, and then if you learn about the Higgs phase, it's often described colloquially as the symmetry breaking phase of matter. But then, of course, the same thing about gauge symmetry breaking, and then kind of acknowledge, okay, it cannot really be broken, but still seems to be like a good description. So one answer, I guess, right, that some people might give is, okay, it's in some sense spontaneous symmetry breaking. Right, with the usual picture, you all see, particle rolling down the hill, and then your matter field getting some kind of expectation value, so to speak. But of course, yeah, that's in tension with the fact that it's a gauge symmetry. So how can something that's an artifact of our description be physically broken, right? So it's a bit unsatisfying, I would say. And indeed, I think as many would acknowledge, a gauge symmetry cannot be broken, but still doesn't answer the question, what is the right way of thinking about the Higgs phase? And, potential other answer is, well, it's actually just a trivial phase. This kind of nicely matches, rather old work from many decades ago, coming from the, I think, originally the gauge theory community, where people were studying gauge theories on lattice models, right? And for example, an iconic phase diagram that came out of that was saying, okay, suppose we have some gauge theory. Let me just be schematic here, right? So there's some tuning parameters. Schematically, let me say there's some axis we can tune, where we couple the gauge field to a matter field, and then we drive up some matter fluctuations schematically. Or there might be another direction where we assign some large dynamics to magnetic fluctuations. So if both of those fluctuations are small, so let's say that the gauge theory will be deconfined. Right, but then, as you can imagine, okay, if there's strong matter fluctuations, a bit like, for example, well-known Higgs model, you enter a regime for another space that is, let's say, called the Higgs phase or the Higgs regime. Another direction, if you have in the limit where matter fields don't enter or not dynamical, but instead you drive some magnetic fluctuations, you can get into the confined phase. And this phase diagram, I'm trying to be static, but what I'm saying now applies basically to the simple cases of Zn and U1 gauge theory. So in this talk, I won't worry about non-abelian gauge theories. Okay, and then the phase diagram that Ruben Verresen found, I guess in the 70s, it looks something like this. So definitely the confined phase is an extended phase of matter, so to speak, using modern language. But then they found that the Higgs and confined phase are connected by an adiabatic path. This kind of, I guess the main takeaway message is that, well, there's nothing much special about the Higgs phase, and this shows it because you can smoothing the form into something that seems very different. And that's kind of underlines what you're saying. It's a trivial thing. Yeah.
In space-time dimensions, are you going to be in for the talk?
Yeah. So many of the statements apply to general dimensions, but typically I'll be interested in the Z2 gauge theory case for space dimensions 2 and up, and then for U1, bump it up by 1. So basically dimensions where the deconfined phase actually is an extended phase. Yeah, but I'll be specifying it when I give certain results. Yeah. But I'll try to follow more interesting setups with gauge theories. The deconfined phase is a stable phase. Good. So okay, so the second picture, this is I can't argue with this. This is a correct statement, and it's an interesting one, and it seems to imply there's probably nothing special with the Higgs phase. But then it's in tension with the first one, like what is the right point of view? In particular, a very physical system that forces us to think more about this. They're actually quite rich. For example, think of superconductors, which is it's essentially a Higgs phase for U1 gauge theory. And it's hard to argue superconductors are trivial. It's in that very rich properties, right? Supercurrent, social Josephson effect, etc. So this doesn't feel like it will be the full story. Yeah.
So I'm sympathetic to the philosophy, but for superconductors, couldn't you just
Sorry, sympathetic too?
So for superconductors, couldn't you imagine the phenomenology you mentioned really just comes from the fact that there's a one-form symmetry, right?
Mm-hmm.
The flux, which you don't have in that picture, which is realized differently in the two phases. Doesn't that account for most of the phenomenology?
Yes. Okay, and then the question still arises: okay, with the one-form symmetry, what is then the phase you're in?
Right. But in the superconductor phase, it's unbroken. In the Coulomb phase, it's continuously broken. Doesn't
Right.
that account for most of the?
Yeah, I mean, I do. Well, yes and no, in the sense of, I think it's it needs to be investigated. What properties do you really need, say, for Josephson effect and superconductivity?
Right.
Is it true that you need those symmetries, and you need them exactly or approximately? And if so, is there a well-defined statement, or is it just a crossover? And,
Right. Okay. So
and
if you break the magnetic flux, if you break the one-form symmetry.
well, yeah, I think those are connected questions. So first, we can ask with the one-form symmetry, you can ask what is the right way of labeling this phase? Is it still one of these, or is it non-trivial? And what concept should we put out with? And then secondly, will the concept help us understand what happens when we break the magnetic symmetry as well? And I'll try to address both.
Thank you.
But yeah, in the U1 gauge theory, the non-Higgs phase, at least the one that we have in the continuum, has a gapless photon. And that's very robust. If you have matter, you won't change it because there's a spontaneously broken one-form symmetry.
I agree.
Yeah.
I don't think anything I said argues against that, though. Yeah.
Okay.
I agree with that.
I have a question I should know the answer to, but I think I've forgotten. In the Higgs phase, there's a vortex. A vortex string in 3+1, and in the confined phase, there's not. So what?
Meaning you could insert it, or what does it mean? Like to say there is a
There's a excitation of which is a topological vortex, and there's not in the confined phase. So what happens to it as you move adiabatically from one to the other?
Right. Also something. Yeah, I think I'll address this as we go along. I think.
Do you assume that I missed? Do you assume that there are dynamical monopoles? Or?
Well, so I'll explore both cases. So that will be going away, from the y-axis, right? I'll explore both cases.
If there are dynamical monopoles, then vortices will not be stable.
Right, but then you could ask, how do these effects we know on the y-axis, is there kind of the topic I'll be addressing is, do things immediately go away or not? I'll unpack.
But there are famously not dynamical.
Well, okay, no. I'm not talking just about superconductors. I'm just talking about gauge theory, right? And then we're going to explore with and without. Yeah. But indeed, it also is a question, suppose our universe has only very dilute monopoles, but non-zero fraction. Will superconductivity be a stable phenomenon or not? Let's see. You're saying no? Sorry. Well, the answer is yes and no. It depends. Certain properties of superconductors are stable. Yeah. But then others are not. Or it's all argue. We can see as we get there. Okay. So, good. And for this picture, this kind of spontaneous symmetry breaking picture seems to, be a good working picture to use to understand superconductors, but at the same time, it's still not satisfying because we're talking about breaking gauge symmetry. What's that supposed to mean? And obviously, we're trying to advocate for a different picture that, is both agreement with all the true aspects of all these, but still, I think gives a more coherent understanding. And that's what I'll try to argue. Good. And actually, to motivate, making a new claim or understanding of Higgs phases, I'll give two clues to why I might expect there to be a better understanding available. So the first clue comes from condensed matter physics, in the sense that, this tension we're seeing here, that there's something interesting to be said about Higgs phase, at least in certain regimes of parameter space. But at the same time, the best available description being in terms of spontaneous symmetry breaking, in some sense of the word, is actually a kind of issue that also arose in condensed matter physics. So there was a similar tension. In condensed matter physics community. Okay. So around the 1980s, people discovered a new state of matter. Basically, people discovered the nice theoretical model is the spin-1 chain. More precisely, what people discovered is, of course, people had thought of this, or knew that this model existed. But then, of course, Haldane famously pointed out that, unlike spin-1/2 chain, is actually a gapped ground state. Okay, it's gapped. And then, as people were studying this, they found that all kinds of interesting properties. So, for example, it has edge modes. So what this means is if you solve the system with open boundaries, the ground is no longer unique. So with periodic boundaries, the ground is unique. With open boundaries, the ground is degenerate. And there's a bunch of interesting rich properties that people found. And of course, naturally, people were wondering how to understand this. And so basically, until, I would say, the early 2000s, people understood it as what they called hidden symmetry breaking. So hidden, I'll use SSB for spontaneous symmetry breaking. And hidden refers to exactly the kind of fudge factors that we also use here, in the sense of, okay, so literally symmetry breaking, what you particularly do, you kind of use non-local variables. So if you do a non-local change of variables of the spin-1 chain, then indeed it starts looking a lot like symmetry breaking. And they call it hidden. For example, instead of a 2-point function long range order, actually a string order, but then if you use non-local variables, again, it looks like a 2-point function. So it's again looked at it as symmetry breaking. And indeed, it accounts for some of the correct properties in the sense that it seems to, if you analyze it with open boundaries, the degeneracy you get in the symmetry breaking phase is correctly the degeneracy you expect for the spin-1 chain. It gives a wrong answer, for example, for periodic boundary condition. The graphs should be unique. And I would advocate it's a bit similar to this tension of understanding the Higgs phase as some quote-unquote symmetry breaking state. And of course, since I was 2010 onward, with the famous work by Jacques Nguyen and others, we understand as an example of a symmetry protected topological or acronym SPT phase. Just to make sure we're on the same footing, an SPT phase, there's many different ways of formalizing it, but I think the working definition, you could say what is an SPT phase, basically defined by the fact that if you don't enforce symmetries, you can basically connect it to a product state. By connect, I mean you can adiabatically transform the Hamiltonian such that the ground state evolves into a product state. And then with symmetries, you cannot do what I just said. And then it turns out that this implies edge modes and present boundaries, etc. And so there's a nice framework and from the field theory side of symmetry, phases can be characterized in terms of their response functions and a few input external gauge field. Good, so it's a very nice concept, and it seems like the right way of describing at least these kind of systems.
So in higher dimensions, can we interpret SPT? In higher dimensions, can we interpret SPT as hidden symmetry breaking?
It's a good question. I think it depends on the symmetries. Yeah, with higher form symmetries probably, than with maybe zero form symmetries. It's a good question. I don't know if people have worked it out. Yeah, I guess people only discovered SPTs once they understood the concept, the higher versions once they understood the concept. So I don't know, in alternative timeline, if they had first discovered the Hamiltonians, what would they have said about it? Yeah.
With this definition, is there anything you need to specify regarding boundary conditions?
So, which are you referring to, just calling it an SPT phase, or?
Oh no, with the being able to adiabatically connect to a product state.
Oh, okay, I see what you're saying. Yeah. No, that's correct. No, with boundaries, yeah, okay, there's a bit of a semantics issue there that you could immediately gap out the end mode, but does that count as a transition? You know, you went from fourfold determinate state to one. But I think it's most unambiguously defined by just saying, let's look at a system at the dynamic limit, and you care about the bulk gap, and you just want to keep that finite. Yeah. Thanks for the question. Okay. So that's maybe one vague clue, you know, that maybe in the same tension, you have the same resolution. Of course, it's not really the most compelling argument, but it's the first step. And a second clue.
Any gap phase is in principle SPT.
Yeah. No.
It's just a question.
Yeah. Okay. Not true.
Well, even a trivial one is an ambiguous concept. You just picked one reference state, which is a product state, but you could have picked another reference state, right? So
Yeah, I mean, we're getting
the question is whether there are two phases, two Higgs phases which are different SPTs. Right? So
I don't agree. Yeah, we can come back to. Yeah, let's not jump ahead to Higgs phases yet. But I do agree. For gauge theory, there's more. You want to make more relative statements. Because in gauge theory, it's not even clear what we mean with it. Yeah. So I do agree there's subtleties there to be. But at least for user matter systems, actually, you do usually have a sense of what counts as trivial. But one can always indeed reformulate stuff in terms of relative statements.
I guess trivial would be, you could define it just as nothing, right?
Yeah, product state is a bit as close to nothing as you can get, I guess. So no edge modes. But yeah. I mean, yeah, I'm not opposed to your point about relative statements, but yeah. For Higgs, let's get there in a moment. So the second clue, which is also maybe why is now, like, okay, if there's really a better picture for Higgs phase, why would we only understand it now, as opposed to like many decades ago? And I think because of the importance of you know, the community now realizes the importance of generalized symmetries. And already was mentioned generalized symmetries. Gauge theories have some natural generalized symmetries. For example, if we have, say, Z2 gauge theory, we can have, say, closed Wilson loops and generate so-called magnetic symmetry, which can be conserved in some region of parameter space. And then also similarly for U1 gauge theory, instead of string-like generators, they look more on membranes. So and then you can measure the flux through a surface, and you could say for any continuous choice of alpha, the flux generates a U1. So here's the Z2 magnetic symmetry. It generates a U1 magnetic symmetry. And so just, I think what some people were mentioning, right, this is kind of the nice way of phrasing the fact that you wouldn't have magnetic monopoles, right, as a symmetry condition. And then, as we know, it also gives a nice interpretation of the confined phases, the spontaneous symmetry breaking phases of such a generalized symmetry, of such a higher form symmetry. And the Higgs phase does not break it. So this generalized symmetry is preserved in the Higgs phase. And then, you know, with the lesson of SPTs in mind, you could ask, okay, but what phase is it in? Because that's actually many different kinds of symmetry preserving phases. So you could ask which SPT phase are you in. Okay, good. So that brings me to key message of this talk.
When you say Z2 gauge theory and U1 gauge theory, you're thinking of the Higgs phase in this.
No, so I'm thinking of a theory which I have these symmetries, like an action,
right.
And then you can ask, are the symmetries preserved or not? But the symmetry statement is a property of the action, right, or Hamiltonian. Right, and then the second, and that's of course, people just appreciate now that there are important symmetries to keep in mind. And then of course we also know that in the Higgs phase, the ground state overall preserves this.
So you mean pure Z2 gauge theory and pure U1, or is it a lattice one?
Well, those are not mutually exclusive, I guess. This is general, like as in both theories have regimes where they have a symmetry. On both on the lattice or on the continuum, you can talk about these symmetries. And of course, they can also be broken if you introduce certain magnetic fluctuations. I'm just saying both theories have regimes where they have these symmetries. And these symmetries can help to understand, for example, deep confinement phase. And what I'm suggesting is, in the Higgs phase, these symmetries are present and preserved. And that's a setting where the next question should be, okay, if these are preserved symmetries, can they protect an SPT phase?
Just to understand, the Z2 case, is that the y-axis of your picture for Fradkin?
Yeah.
Yeah.
That axis has it.
That
Yeah. And by the way, I mean that, yeah. Similarly, that picture also holds for U1 and 3+1D. And then, yeah, now I'm talking about this one.
Great, thank you.
So the key message is that in the gauge theory, and actually in this talk, I'll be talking about either say Z2 or U1. The Higgs condensate, and I'll be talking about the simplest case of a unit 1 charge. Unit 1 charge Higgs field is a non-trivial SPT phase. Of course, then the next question is for what symmetries, right? Because the SPT phase is only meaningful when one refers to symmetries. Should I write it? Protected by, first of all, the higher form magnetic symmetry that I just mentioned. And, let me put it in quotes for now, something I want to call the matter symmetry. The name is supposed to refer to it's some charge related to the matter or Higgs field. In this talk, matter and Higgs field are the same to me, it's just it's a field coupled to the gauge field. And of course, I put it in quotes for the obvious reason that I need to clarify to you what I mean by it. Well, right. Because at face value, you might say, okay, the matter field, by definition, I guess it will be charged in the gauge symmetry. But I don't want to call the gauge symmetry matter symmetry because it's not physical. Right? So I am talking about some physical symmetry, but I need to clarify to you what is that physical symmetry. But and I'll clarify it, but condition of clarification, this will be the statement.
So will you talk about when these symmetries are emergent and when they're not, and what's the importance of this?
Okay, yeah, I'll talk about both. So, in the clearest cut case is when they're exact symmetries. Yeah, and then I'll talk what happens when you slightly break them.
So this statement is a non-trivial SPT. If you explicitly break both, I guess it's not going to be non-trivial anymore in general.
Yeah.
If you only break one of them, badly, let's say, then does it stay non-trivial?
Yeah, it's a good question. The cleanest statement is you really need both symmetries to have a well-defined SPT.
Okay.
But what is true is that when you break the magnetic symmetry, the effects are parametrically stable. And I'll clarify what I mean.
That makes sense.
Yeah, but I would no longer call it an SPT phase, but its effects are robust. But we'll get there. Yeah, so it's an important question.
You mean it's approximately robust in some regime, or?
Yeah, I'll wrap what I mean. It's a bit of a subtle thing, yeah. Right.
Oh, by the way, just want to make sure. Does this statement generalize to other gauge groups?
Yeah, I'm not sure. So far, I've personally only thought about the abelian case. I do know Röntgen, have a better understanding of the non-abelian case, but I haven't made it as far as he has.
By electric magnetic duality, should I expect that the confined phase is also an SPT for some other?
Yeah, that's true. You could kind of carry over the discussion. That's true. Yeah. I'll just focus on the Higgs phase concretely.
I wonder, I mean, there are these, I don't know how familiar you are with these models I studied, but you could in principle put both, well, he said he looked at the papers, but you could in principle have both magnetic and electric matter with global symmetries.
Exactly.
And I'm wondering whether some Higgs phases, because, you know, then you would replace the one-form symmetry with some global symmetry of the magnetic matter. Maybe there's an SPT hidden there. Even if you have magnetic monopoles,
I see.
they have a flavor symmetry.
Yes, I see what you're saying. Yeah, I don't. That's a good question, and I don't think in that case it'll be non-trivial. But yeah, we did use your models to also write down a model. In our paper also, when we discussed the UN case, which is the second paper up there, we also discussed on the lattice where we use your work about having exact magnetic symmetry on the lattice, and then we have exact SPT statements also on the lattice. But yeah, still with the higher forms. Was there another? So then, three natural questions when you see this are, first off, is this meaningful? Is this a meaningful statement? Especially because of this suspicious quote-unquote matter symmetry, right? Is this meaningful? Once I convince you it's meaningful, the next question is it true? And once I convince you it's true, forget that part. You can also ask, is it interesting? Should you care? And I will do my best to address all three. In fact, let me straight away comment on the elephant in the room, right? Is it meaningful? In particular, I think, hopefully, if I convince you this part is meaningful, then I guess hopefully the rest is meaningful as well. So let me focus on what do I mean by matter symmetry. So let me give some comments on this first one. So the nicest case is where we add a little bit of extra structure, which then at the same time emphasizes not necessary, but it does smoothen the discussion. Nicest case is if we have two or more Higgs fields rather than just one. So it's a bit related to this moment that having two Higgs fields, we can actually compare the two different SPT phases they're in. So for example, let's call them phi A and phi B. Right, so let's say they're both coupled in the same way to the gauge field, unit charge, to Z2 or E1 gauge field. Okay, and now, note in this case, there's a very simple meaning to what we might call a matter symmetry, which is basically conserving the field separate. And that's not just the gauge symmetry, right? For example, now matter symmetry would be, let me just call it NA minus NB, maybe divided by 2. This is an integer valued physical conserved quantity, or can be if you preserve the symmetry, right? So to convince you, the way to know if a symmetry is physical, right? What you want to, I should be able to write a local gauge invariant charge on X, right? So e.g., for example, phi A at X bigger, phi B at X is local. It's gauge invariant, but it is charged. Charge 1 under this symmetry. So in this case, it's a very unambiguous bulk symmetry that we can associate. And it fits the matter symmetry, the circle. It's related to something having to do with the matter fields.
have a question about this. As soon as you do this, if you don't add phi A dagger phi B to your Lagrangian to break the symmetry, if the symmetry is really there, then this is just a global symmetry breaking, isn't it? Or zero-form symmetry. The Higgs phase is the phase where that global symmetry is continuously broken.
But what do you mean? What do you mean by the Higgs phase?
Well, when these things are condensed, what do you mean by that?
What if I only condense one of the two?
If you condense one, then it's not broken.
I think you would have some challenge to condense it. Like imagine trying to do a semi-classical calculation and try to condense one. You're going to have some trouble because, well, can you?
One of them, I think it's fine.
One of the masses is negative, the other one won't condense. Maybe not. Yeah, maybe I'm wrong.
Right, so we'll get to that exactly right now. So you can imagine, I'll continue here. So indeed, it's a physical symmetry. So what does it imply? So how much detail want to get at this point? I get lost. Okay, so what is an implication? Let me put an asterisk so continuing from there. An implication, which is an example of why you might think our statement is interesting. Question 3 was, is it interesting? So, so implication of having that physical symmetry and moreover this key message implies that the two different phases should be different SPT phases. Okay, so it means that, for example, suppose now you have another schematic phase diagram where you have some deconfined phase. And now, say I have phi A fluctuations that can drive a Higgs phase, and phi B fluctuations. So here,
this is phi B condensed, phi A
yeah.
condensed.
So then, so here we have, say, the Higgs for the A field, where you might say, phi A is non-zero to the extent that you want to make sense of that A. And then here we have a Higgs for B field. Actually, the statement is they cannot be connected. There has to be an SPT position in the bulk. Which is protected by the physical matter symmetry and magnetic symmetry. Yeah?
I think I should have asked this before. What do you mean by the deconfined phase with charge 1 matter? What does it mean? How do you define it?
It's a photon, Coulomb phase.
Well, depends. I didn't. This statement actually works both for U1 and Z2. But yeah, for each one, let's say U1 for concreteness, yeah, this is a Coulomb phase.
Coulomb, that's what you mean.
Yeah. And for Z2, it's, Z2 deconfined. Condensed matter topological phase. Z2 topological, whatever you call it. Okay, good. So that's a first non-trivial consequence from this statement that they differ by some SPT response function that requires a transition. Of course, it doesn't have to be direct transition to intermediate phase. The main point is they cannot be connected. What precisely happens depends on choice of model. Yeah.
But and I'm coming back to my earlier question. I mean, wouldn't you expect that along that line is where the symmetry that you just introduced would be spontaneously broken? Because that's the line along which they have the same effective mass squared.
Yeah, okay.
So you would expect their spontaneous symmetry breaking.
No, that's fine. That's fine.
Line, there should be a phase.
I mean, it depends on microscope. But okay, I agree. In this regime, there should be a symmetry breaking. Yes. I mainly want to focus on these not being connected, but yeah, this is correct. So I'm not trying to argue that this region is universal. The main point is there can be no gap bridge connecting them. The rest will depend on.
There could be even a phase between.
Yeah,
right?
yeah.
It's just that you cannot.
Yeah.
Without,
they cannot be connected.
without closing the gap.
Yeah. Good. Even though both, they seem featureless. Like if you're in this one, you actually cannot tell by doing local observables. Very much like SPT phases.
Is this basically the consequence? If you preserve a Z2 symmetry which interchanges the two Higgs fields, then there is a 't Hooft anomaly involving the U1 symmetry, which is the relative phase of the two, the exchange symmetry, and the magnetic one. Ryan was on this paper with Zohar.
Right. I mean, I'm not reinforcing a duality symmetry.
I understand, but that's the fact that they're in different SPTs is related to that because the SPT counter term
but it also
generated by the Z2 exchange.
That's an alternative perspective. I mean, that's also SPTs. often when you have two different SPTs at a transition, you get an immersion duality, which by virtue of having different SPTs is anomalous.
That's right.
So it matches.
That's right.
So it's not, yeah.
But
It's,
that's
it's
basically.
complementary. Yeah.
I mean, one can see that they must be SPTs because of the total.
That's not always the other. One way always works that having different SPTs implies that the transition usually has some kind of immersion anomaly, but not all immersion anomalies have to do with different size being SPTs. So, for example, knowing there's a transition doesn't itself tell you that a spatial interface between these two must have edge modes. But that's also a true statement by virtue of them being different SPTs. But you can find other systems, the lattice systems, forget about gauge theory, where you have some anomalous critical point between two different, well, seemingly different gap phases. But in the broader phase they're actually connected, and then the spatial interface between these two phases doesn't have a connected edge mode. So, yeah. It is a true statement of the anomaly, but I don't think it's equivalent.
But I thought that you could think of this transition as interchanging adiabatically to gauge fields, and then you can apply the Z2 transformation and generate a counter term, and then you see that the SPT counter term is different. I think you can show it this way. This is coming basically from the anomaly.
But that anomaly is not the same anomaly as characterizing the SPT.
Okay.
Yeah.
Okay. Well, we can check. I think you can see it from the anomaly, but I'm not sure.
Yeah.
We can check later.
Okay.
In this example, you would expect the transition line between the two SPTs to be first order, right?
Well, that depends on circumstance. Actually, I'll give you a model where it's a.
3+1.
Yeah. 3+1D probably hard to. Yeah. But I'll give you an example 2+1D where you actually have a continuous SPT transition.
But it's not necessary for there to be
No. Again, I'm trying to emphasize the main point is they cannot be connected. Any extra information about the nature of the transition, if it exists, like the direct transition and the nature of that fixed point, that's all circumstantial. Other than it must have an anomaly.
So if I introduce phi and phi b in principle, there are many types zero form symmetries I can add to phi and phi b. Do you mean for any choice of those matter symmetry, this statement is necessarily true?
Yes. At least for abelian, I haven't really worked much about non-abelian cases, but you can add some spin, matter field with some spin degree of freedom, and then.
For example, I can consider a symmetry that just exchanges A and B, phi and phi b.
Oh, I thought you want to assign a charge to the field. That is more like having a dot. Okay. Yeah, let me think about it. The simplest case where it definitely applies is there's some notion of a U1 conservation, like U1 for U1 gauge field and Z2 conservation for Z2 gauge field. So yeah, let me put aside considering any possible symmetry. I don't think I can work it out like so. Let's chat about that.
So for U1 gauge theory, you require the additional symmetry. Is U1 instead of something else?
It might also work for a subgroup of it. But let me first focus on the simplest case where there's some kind of interpretation as U1 conservation. Yeah.
Can you say a bit more about the matter symmetry over there? Like what actually it does? It's just something that transforms this composite operator object, or is that it?
Basically, physically, it means that you're not allowed to transform one field into the other. That if you create a phi A excitation, it cannot dynamically transform into a phi B excitation. You can count them separately, and they're conserved under dynamics. That's the you don't look at it. So.
In this particular case, it's a relative phase of the two Higgs.
So they both charge on the U1 symmetry that was gauged.
Yeah.
So it's no longer there, but there's still some.
Yes, there's a relative phase, which is a global.
Yeah, which you could break by virtue of being an actual symmetry.
And so like you say that Higgs phase is the one where this matter symmetry is broken, or it doesn't matter?
No. The Higgs phase is not symmetry breaking. It's an SPT. So nothing is broken. Here or here.
Well, I mean, depends on what you call a Higgs phase, but
yeah, I would
he
say
defines
both are
it.
condensed. I would call it a Higgs phase.
Okay, that's fine. Yeah, fine. That's fine. But
I'm really confused. What is Higgs phase right now? Like so, operator condense. This composite operator phi A, phi B condense and have non-zero.
But let's condense only one of the two.
Okay.
Yeah, that's the situation I'm talking about.
Because then the order parameter of this U1 symmetry breaking is a bilinear in the two, and that does not condense, but only one condenses, and so it gaps out the gauge fields. It doesn't break any symmetries, but depending which one you condense is different SPTs. This is
I see.
Yeah, and of course if you break both, now you lost the physical matter symmetry, and the SPT is no longer well defined as usual. If SPT and you break some of the symmetries, the SPT class. But if you preserve the physical symmetries, magnetic and matter symmetry, you get well defined SPT class.
I mean, just a comment, because it helped me yesterday, you explained this to me. Naively, semi-classically, you cannot indeed go from one condensing to the other condensing without closing the gap, because if they both condense, then you break a U1 symmetry.
Yes.
And if neither of them condense, then you go to some other transition. And so semi-classically, there's no path.
Yes.
So it's very plausible.
Cool.
That argument.
Yeah. And of course, as I said, that's the nicest case. And nice in the sense of, it's the least subtle. You have a bulk SPT position possible. But again, I want to emphasize, you don't need multiple Higgs fields to make sense of this statement. Okay.
Do you always need complete Higgs?
Do you always need what? Okay, that's also a good question. Thanks. Complete Higgsing, I guess you mean, for I have a unit charge, right? Instead of I could have a charge 2 Higgs. So then it's an SET. It means it's a symmetry-enriched topological order. So then you have coexistence of a deconfined phase, but on top of that deconfined phase is symmetry-enriched by the same SPT physics. And everything carries through. It's just a bit annoying that you have to take, always do bookkeeping for both. And in fact, physical superconductors are, strictly speaking, not SPTs, but SETs for this reason, because they're actually charged 2 condensates. But all the physics of Josephson effect and superconductivity arise from the symmetry-enriched part, and actually the Z2 topological order or deconfinement is kind of circumstantial, I would say. Or this is pretty subtle to pick up that part. Good. So what about if you only have one Higgs field? What could be a meaningful notion of a matter symmetry? Right, but at face value, it sounds like you just have the gauge symmetry. Right? The definition of the Higgs field is charged under gauge symmetry. So any naive fashion of defining a matter symmetry sounds like it's just talking about the gauge symmetry, which surely cannot do anything interesting. Okay, but it turns out there's situations where you can still have a physical matter symmetry. Example, let me talk for example. There's still a physical matter symmetry. E.g., it's supposed to be the only case, but if we have some defect in our system. So for example, now this is not a phase diagram, just space, say x and y. And let's say my system is in the Higgs phase, right? So locally speaking, phi is non-zero. Phi is non-zero here as well. Sorry. But now I insert a lower dimensional defect, which is defined by the property that the charge cannot move across it. Okay. So let me call it a no tunneling defect.
How do you define that? That the current is 0?
Yeah, well, okay, one way of defining it is by virtue of defining a physical symmetry. Let me define a symmetry that is a consequence of this, and you can take that symmetry as a definition of what it means. But first, okay, let me also answer on a lattice gauge theory. On all those bonds, you tune the charge hopping to 0. That would be a microscopic example. But what it means is if you look at the, say, the left-hand side of the system, relative charge, say the charge on this side is conserved.
Are you referring to gauge charge?
No. Well, okay. The thing that starts out with gauge charge, let me just write it down. The charge on the right of this defect minus the charge on the left, and again divide by 2 is for getting as integers. This is physical conserved quantity. Again, to convince you it's physical, let's write down a local gauge invariant charge object. Dagger, phi, and let's add a little Wilson line to make it gauge invariant. Okay, so this combined object is local, it's gauge invariant, but it's charged. right? Picks up a charge from one and puts it to the other, so charge 1 on this thing. And the way it seems physical is I can destroy it. Right? I can allow hopping and now it's gone. As in, like any physical symmetry, it doesn't have to be there. Okay. So this is a situation where there's now again a physical meaning to having a matter symmetry.
So in this situation, if I fold it, it becomes the previous case, right?
Yeah, you can think of it like that. I hadn't thought of that. That's nice. I guess I have to think. Or do you have now two different Higgs gauge fields coupled to them? Because the folding, you also fold the gauge field, right? So you actually fold the gauge field as
You have two different gauge theories on the two sides, yeah.
Yeah, so it's not quite the same as the previous, because that had one gauge field.
No, there's still one gauge field, yeah. but the matter fields on the two sides are just different now.
The gauge field can propagate through, right?
Yeah.
Can it?
Yeah, the gauge field can propagate through.
There are two gauge fields, but they somehow are
yeah, I guess. Maybe the basis chain. Okay, let me know. Yeah,
is it kind of the same, because it's like gapping out one of the Higgs fields on the left, and then gapping out the other on the right completely, and then declaring these two different ones to be the same, but the charge cannot flow because they were really different. It's almost sounds like your previous case where the mass.
I mean, I can write down a model. It's let me say it like this: in superconductors, people do this. Even if they have one phi. It's called the Josephson mark. But you don't have to think of two fields. It's a dynamical. We impose a symmetry.
No, I understand that, but I think you can get this case from your previous case by some limit.
Yeah, I see. Yeah.
If you declare them to be different, then automatically the current will not flow.
Mm-hmm. No, that I agree with. Yeah.
And then you can just gap out.
Yeah, it's like a weaker version of the thing which doesn't require two fields. Yeah. Cool. Okay, good. So now you have physical matter symmetry, and again, the claim is the magnetic symmetry together with this physical symmetry protects a non-trivial SPT phase. And what is the consequence? An implication is that now this defect looks like the edge of an SPT. So you have an anomalous symmetry action on the defect, where the magnetic symmetry together with the matter symmetry is acting anomalously. Okay, and yeah, so I mean, keep it at that abstract level, but maybe I can tell you if it sounds a bit arcane. Let me tell you this exactly how to explain the Josephson effect as an SPT phenomenon. So it turns out in condensed matter we know this as the Josephson effect.
What is anomalous symmetry action?
These two physical symmetries, the way they act in this region, is like an anomalous action. So if you were to describe the field theory on this edge, you would see there's an anomalous action where those two symmetries have an anomalous response function. Yeah. Yeah. Anomaly for these two symmetries.
Can you just say a little bit more when you say explain the Josephson effect? What specifically you want to explain?
Okay.
The current.
Yeah. Well, so there's I guess multiple Josephson effects. You know, like AC and DC, and all of them you can explain by this. But I mean, the simplest one, for example, the fact that the Josephson effect is the fact that you have a superconductor, and then if we initially have an insulating region, then we allow perturbative hopping, that the current is proportional to the phase difference of the two sides, right? Then you can derive from this. I was going to say a bit more about that, but about it later. Now just more maybe teasers.
So in that case, the tunneling is there.
Yeah, good. Yeah, so then it's a consequence that you have an anomalous theory, and you add a perturbation to it, and from the anomaly you can derive the effect of the perturbation. But it's a consequence of having the anomaly. But also some of the Josephson effects don't require the tunneling. Yeah, but shall I get back to the Josephson effect?
Maybe we can discuss later, but one thing that slightly puzzles me is the Josephson effect you have tunneling, so you've broken the symmetry.
Yes, that's what I was just saying, is that the SPT tells you that this is anomalous. So before tunneling, the Josephson junction actually turns out to be anomalous. Like certain symmetries have anomalous on it. And that anomaly implies that if I now perturb my action by a small perturbation, from that anomaly I can derive the consequence. But to be clear, some of the Josephson effects don't require tunneling. I think like the AC one doesn't. So you don't need to do the extra step, but the most familiar one is this one, where you allow some perturbative tunneling.
But are you saying that even though the anomaly is no longer there, when you allow tunneling, that the effects?
Yeah, it's like a kind of a linear response theory, something like. From an anomalous theory with a certain perturbation, you can derive certain non-trivial effects. Even though, strictly speaking, with the perturbation is no longer. This is
right, but it depends on the phase of the defect, how you saturate the anomaly and the defect. If the anomaly and the defect is saturated by gapless modes, then
okay, that's a good question. Okay, we're getting into the weeds. This is true. So some of the anomalies are independent of how the state is realized. Others actually depend. But the type of anomaly I'll discuss tends to favor one type of phase. Yeah, but some of the Josephson effects are true independent of how you satisfy the anomaly. It's really an anomaly statement.
Yeah, the ones which don't require that.
Yeah. Cool.
I'm going to talk about what anomaly do like this.
Yeah, okay, I can already say. Basically, maybe I could just mention here the SPT response function. So let's say A is an external gauge field for the matter. So A math is for the matter. A is for the magnetic symmetry. It's the simplest thing you could have guessed is this kind of mixed response function. So in particular, so I've written it down for the U1 case. So in 2 plus 1D, this is known as, in condensate communities, form spin Hall effect. That is because 2 plus 1D, the magnetic symmetry is a global symmetry. So that's 0 form times 0 form SPT. This is quantum spin Hall, it turns out. And in 3 plus 1D, it's a 0 form and 1 form mixed SPT. And with an anomaly defined by this, and you ask, what is physically the edge of that SPT? Right? In 2 plus 1D, people know at quantum spin Hall, the edge is a kind of a compact boson, 1 plus 1D compact boson, where the U1 times U1 anomaly is the one we're all familiar with, I guess, by shifting the two conjugate fields. Let's talk about the more interesting 3 plus 1D case. You can ask, what is the anomalous state on 2 plus 1D edge, or the natural one consistent with the anomalies? It turns out that it's the 2 plus 1D superfluid state. That actually, I think Luca was the first to point out that 2 plus 1D superfluid, actually, of course, we know that eventually has U1 symmetry breaking, but actually there's an anomaly characterization of the state. In those cases, there's an emergent one-form symmetry, keeping track of the winding of the vortices. And the global zero-form symmetry of superfluids, the one that's spontaneously broken, together with the emergent one-form winding symmetry, have a mutual anomaly in a superfluid. And from that, you can derive various kind of dissipationless currents in superfluids, etc. This is a nice anomaly statement. And it turns out the SPT I'm talking about is exactly the higher dimension SPT of which the edge would be a superfluid. That's it. Okay. Okay, so maybe before the break, the last thing I want to point out before the break is some comments about 3. So far, I did my best to give you some sense of in what situations the statement is meaningful, where you have a meaningful notion of matter symmetry. But then, okay, why do all, if we have to do the effort of convincing ourselves it's meaningful, is it worth something? Do we get to learn something interesting? And I guess, I already, okay, let me write it down. So I'll briefly make some comments about potential reasons to be interested before the break. So, well, I guess we already saw an example that perhaps interesting to some. Is it on the back here? Right? That if you have, that for example, here's a bulk SPT transition or intermediate rings, etc. if we have multiple Higgs fields. Right, the more precise statement is the phi A and the phi B condensed phase are not connected. So that's the one I already discussed. That's maybe the most easily digestible example. Good. Also, I think a nice understanding of superconductors explains superconductors. So I already hinted at the fact that some of the anomalies supposedly explain the Josephson effect. I mean, I know I haven't gone into detail, but that's a claim. And also, another famous effect of superconductors is the name superconductivity. And it can also, it turns out, be understood as the SPT effect. Again, spoiler, and I'll try to say something in the second part of the talk about that, is that superconductivity, once you interpret in this SPT picture, it turns out it's a topological Talos pump. And for the familiar Talos pumps, we know that's something that uses topology in some kind of parameter to transport charge, and that topology is protecting the supercurrents. Okay, so I'll try to come back to the second part. And one fun reason, of course, we already know superconductors. We know they have superconductivity and Josephson effect. Okay, why then care about an SPT interpretation? Well, for one, I would think it's kind of the most, how to say, fundamental understanding in terms of it's very directly related to the symmetries that are necessary, and it's directly from those symmetries you can derive it without worrying about actions that one got. But also, it suggests potential ways of generalizing the phenomena as more, and once you know what the properties of this SPT that gives superconductivity, you can export other SPTs and see if you can find similar phenomena there. Kind of generalize it through the SPT point of view. And then the last thing I want to mention before the break is, I think I was asked already at the beginning, like, do I want these symmetries exactly? Right? What if we violate some of the symmetries? In particular, as we know, depending on the circumstance, having a magnetic symmetry is a bit fine-tuned, right? If you have a lattice gauge model or whatever system you're interested in, you might have monopoles, right? And if all of this requires a special limit, it would have limited applicability. But it turns out that it has implications even if we break magnetic symmetry. Right, so in one case that means if we would allow for monopoles. And also kind of touches this exact thing you would want to know, kind of touching on David's question earlier on, like what happens to superconductors once we allow for monopoles. And once you interpret as SPT effect, you have like the right setup to explore that if you break magnetic symmetry. And then in particular, it's robust, magnetic symmetry. In particular, some of the effects. For example, this anomaly thing I was mentioning about this topological effect. The effects are robust for if for Z2H theory, it's basically dimensions when it's higher from symmetries, right? As you might expect. So D is my spatial dimension, so 2 and up, and for U1, 3 and up. And then the last picture I'm going to draw is kind of the version of the usual Kretkin-Schenker phase diagram, but now in the presence of such a defect, right? So, Kretkin-Schenker were of course correct that the bulk is adiabatically connected between these two regimes. But now you could ask, what if I interpolate this phase diagram in the presence of this kind of defect? Okay, where I have this little region where charge cannot move. It turns out, okay, let me first draw the bulk lines. That will of course remain true. So let me draw the Higgs regime, the confined regime, and the deconfined regime. That's the bulk lines. So maybe on top of those bulk lines, there's a boundary or defect phase transition. So in this region, you have an anomalous interface or defect line. This again, I'm referring to the setup behind the board here. This setup here. Right, so we have this tunneling defect and we tune the Pollock phase diagram parameters. And the anomalous state is robust in this whole regime. And eventually, there is a lower dimensional transition, meaning lower dimensional is only along this line that system go critical. And then after the break, I'll discuss first the Z2 case where we can actually, in some sense, solve the system and actually confirm it. And then I'll discuss the implications for one. Okay, let's take a break. And 10 minutes?
Yeah, 10 minutes, okay. Can you keep the time? Don't forget. I think you have the same thing even I'm sorry, yes, I'm supposed to do something.
No.
But, you know, okay.
Cool. Right. It's kind of like an empty break for me. It was like more questions. All right. Good. So I think so far I try to give you the taste of the general claim and implications, but at a very nature of me trying to be a bit schematic and, you know, to give a sense, it was also a bit vague, right? So what I now want to do is be a bit more concrete in a setup where all statements are clearly well defined and, you know, we can talk about statements and the setup. So and also because I'm a bit of more of a lattice person, let me consider 2D Z2 lattice gauge theory. And even if you're just interested in U1, many of the U1 statements have analogs in the Z2 case. But yes, it's simpler to discuss about things here on the lattice for Z2. So yeah, let me focus on that. And in particular, I'm going to focus on 2 plus 1b. Okay, so our lattice geometry will be something like this, where we have 2-level systems, qubits living on bonds and sites. And so each of those degrees of freedom has some poly matrices, and just to make the notation, you know, not so heavy-handed, I'm going to use different symbols. So X, Y, Z for the poly matrices on the sites, and the usual poly notation, sigma X, sigma Y, sigma Z on the links. I have my full Hilbert space that tensor, initially a tensor product of these sides, and then I want to enforce a Gauss law to make it a gauge theory. So the Gauss law will look as follows. For every vertex of my lattice, I'm going to enforce that acting poly X on this side, and the poly X on the 4 bonds is +1. Right? So the Gauss law tells you that the matter charge, the parity of the matter charge equals the electric flux radiating out of the bond, right? Okay, good. So let's explore all of the general stuff I was saying before in this particular setup where everything's nice and clean. Okay, and so let's write down a natural Hamiltonian with all the physics we're interested in. So what could be that is gauge theory Hamiltonian? First, for every vertex, I'm going to have a poly X on the sides. Basically, physically, this penalizes the presence of mass, like a mass term. Okay, so if you use this term, there's no mass excitations. It's pure gauge theory, so to speak, if this term is strong. And then you have a term that kind of penalizes magnetic excitations. Right, so a little plaquette, like a Wilson line on a plaquette. If you just have those two terms, the ground state would be the deconfined phase of the gauge theory. And now we're going to add two perturbations similar to this schematic Fredkin-Schecker phase diagram I showed before. One will be assigning dynamics to matter fields, or matter, whatever you want to call it, excitations. So it'll live on bonds. So I'm just drawing a little piece of the lattice here. So not an H, it's just a piece of the lattice. And so it'll be a 3-body term, poly Z on the sides. So you should think of it as like a psi negative psi and a little Wilson line sticking between it to make it gauge invariant. This is hopping for charge. And then lastly, we're going to also add a term that allows for fluctuations of the magnetic region of freedom. So there's going to have to be something that doesn't commute with this, so it can create magnetic excitation fluxes out of the vacuum. So it'll just be a single-sided term that lives on the bonds. So again, let me draw a piece of just to emphasize, say the red is a piece of the lattice. Oops. And then here is sigma x. And you see that acting on the ground state, it'll flip this plaquette and this plaquette. So it inserts excited magnetic excitations that change the sign of the Wilson. Hope everyone's. Let me know if, let me know if someone's on board. But Just the usual application to the Hamiltonian.
What's the gauge symmetry here? Z goes to
The gauge symmetry, well, basically you could say, okay, gauge symmetry, how to say it?
the generator should be your Gauss.
Yes, exactly. So, you know, I can just maybe say in words. What it does is it flips. If you think of qubits, whatever you call it, spins in the diagonal basis, 0 and 1. And with the Gauss law, will flip, like insert or remove matter, so to speak, and it will flip the electric field line sticking out of it. This is the operator notation for it.
And the magnetic field is invariant because it commutes.
Okay, yeah, good. Okay, that's what I want to say next. So, if H is 0, then we have magnetic symmetry. So if H is this term, if this term is not present, then we have magnetic symmetry. Generated by, let me call it Wilson loop. So for closed loops along the bonds of the lattice, basically, broader versions than this guy, they commute, right? You can just ignore this. Everything's diagonal in the sigma z facing links. And then, of course, if H is not 0, then we have dynamical magnetic matter, whatever you want to call it. Fluxes. Yeah. Or whatever you want.
Magnetic symmetry plus 1D is supposed to be a 0 function?
No. Maybe think of U1 as the case.
Okay, so it's a different magnetic symmetry.
Well, it's for C2 gauge. Yeah, so the one I was saying, yeah, this one. The field theory is the Wilson loop.
Is there a field theory analog of this theory?
Yeah, undoubtedly. I'm just more of a lattice person, so I'm not going to try to write it down.
Okay.
In the deconfined phase, I mean, it's just like B wedge DA with 2 gauge fields.
Oh, right, that's the. Okay.
Yeah, and in the other phases.
With 2 matter fields.
You can couple matters of
that would be.
Okay. Good. So that sets up the physical system. Right. And just to get our bearings, so let me just add a general Frankenstein phase diagram, which should apply in this case. And these people did numerics to work out what is the precise structure of the phase diagram of this model. So let me say phase diagram with periodic boundary conditions, or infinite plane if you wish. Looks as follows. So we have H and J. Just like before, I was a bit vague. This was matter fluctuations, magnetic field fluctuations, but now we have the Hamiltonian can be very concrete. Large J is going to be drive a Higgs phase. Large H is going to be a confined phase. There's a Higgs regime. There's a confined regime. And then we have a deconfined phase. And then the precise phase diagram, this is due to Julian. I think the first results I know numerically are Julian Vidal, and also separate work by Tukbits. Probably writing his name wrong. In the 2010s or so. So they figured out the phase diagram numerically. There's a multi-critical point, which is kind of interesting. First order line, Ising critical point. And then this is 0.33. And of course, the precise is not important, but just I want to give you a sense that people have kind of fleshed out the precise structure, and there's no surprises. Other than this multi-critical point, but that's not the focus.
Yeah. Without the boundary, it's equivalent to Kitaev model, right?
Can you say it?
Without the boundary, this Hamiltonian is equivalent to Kitaev model. Is it correct?
Yeah, that's correct. Yeah, indeed, that's what they said. Or at least in one of the 2 works. Yes. Yeah, just to repeat, Max was pointing out that yeah, for the periodic boundary condition case, you can actually map the model to toric coordinate field. That's why I was starting from the correct matter point of view.
What goes wrong when you try that with the boundary?
Well, yeah, I'll get to the boundary next. Yeah, but turns out there's an extra bookkeeping you need to do. Like, it's not a one. Okay, you could. Okay, I'll get that.
So it's a straight line Ising, or is the end line?
These lines are gauge Ising.
Gauge
Ising mod Z2. Both of these lines.
And then the point is.
People don't know topological.
Oh, I mean, there are 2 points. I mean, both points are.
Oh, this is Ising.
Oh, that's that.
Usual Ising. I bet people don't know.
What's the dotted line?
That's the first order line.
Isn't this all 2 model?
Say?
Isn't this all 2 model at that point? Critical O2.
The exponents look like that from the most recent quantum Monte Carlo studies, but I don't think there's a field-based proposal for, how O2 would be described. Okay, this is not the topic of this talk. I agree, it's very interesting, but okay. So claim 1 is, I guess I want to be precise here. If h is 0, so if we're on the y-axis, then the Higgs, and if you want to mean by Higgs, now I very concretely mean this region here. And the Higgs phase is a non-trivial SVT. Now, of course, I'll unwrap this in a moment. And then claim 2, if h is non-zero, how shall I phrase it? The effects, the kind of consequence of being an SVT, are parametrically robust. And also, this is a vague version of what, and I'll try to be more concrete now. So, for instance, well, okay, let's get there. But that'll be what I'm working towards. Okay, to try to convince you of both of these points. And it'll give some, modified understanding of the differential checker phase diagram in the presence of either defects or boundaries. Okay, so naturally, let's first look at the h equals 0. Let's first talk about the h equals 0 case and see first in the bulk that there's something suggestively looking like an SVT. But then because in this model we only currently have one matter field, just like the case we discussed before, it's a bit more subtle to detect a non-trivial SVT because the gauge symmetry is kind of in the way, so to speak, but we can make it, we can manifest it. And it'll give a more concrete version of what I just discussed, in case it wasn't known. If that was too schematic before with this nocturnal defect and stuff like that, we could be very concrete here. Good. So let's consider, let's have h equal to 0 for now. Then this region, we call it in red, and just literally the line, and not trying to fatten it. That line is a non-trivial SVT with a string order parameter. So the Higgs phase, or Higgs regime, if you want to put the word phase on there, has what I would kind of call an SVT order parameter. Okay. So, definitely coming from this matter physics community, we're used to identifying SVT phase in terms of some non-local order parameters. And then information is actually kind of equivalent to the SVT response functions that one usually studies more from the energy point of view. So what does it look like? We again use red to denote the lattice in the background. So I'm going to focus on the line of my lattice. Okay. And I'm going to take my expectation value of an object. And the object is basically a Wilson string, an open Wilson string, which is decorated with matter charge. Okay? And so one can argue that this is non-zero. More precisely, if I take the long distance limit, the limit first take a thermodynamic limit, then take a string function, a string correlator of distance I minus j. Let's take that to infinity. The expectation value tends to a finite non-zero number. And so first of all, how should we think of this object? Well, to have this non-zero, it's important that we have h equals 0. Because when H is 0, we have exact magnetic symmetry. And note that this string is kind of made out of the magnetic symmetry generator. Okay? So it's the open version of the closed symmetry generator. And because the symmetry is conserved, you can argue that an open version of the string has to have long-range order. I won't try to go into the argument in detail, but one can, yeah.
What exactly is magnetic symmetry?
Yeah. Yeah, sorry. So it's basically for any closed loop along the lattice, say the particle state was these. Strings of just a bunch of polys along the bonds. That commutes with them opponent H is 0. Right? And so you can argue, by virtue of it being a symmetry and by virtue of the ground state being gapped, you can argue that this thing has to have long range order. But we know that it turns out it only has long range order if the endpoint is dressed by a matter charge. And of course, it's enforced by having Gauss law, actually. There's not much choice. But that's the very reason, okay, I want to interpret it as a non-trivial SPT order parameter, and the fact it's really implied by the Gauss law is kind of inevitability of, in some sense, the Higgs phase being SPT. Was there a comment?
Why doesn't it break?
So can you expand your comment? It being...
break.
Why doesn't it break?
Yeah.
Well, it's a correlation function. Or, why doesn't it break?
It's not confined. Yeah, this is not confined. This is okay.
Is it important that it's open, that you didn't draw?
Right. Yeah.
So you just charge under this magnetic symmetry?
So this is made out of the magnetic symmetry generator.
It's not charged.
No, it's not charged. But the endpoint is charged. Well, okay, now the question becomes what you would want to say. The statement you would want to make is that this is an endpoint. And when I say that endpoint carries charge under the inner symmetry protecting the SPT. Okay. But as I spent the whole last hour talking, what does that mean? Like, clearly, what is the symmetry under which this is charged? Well, one is Z is charged with gauge symmetry, but we don't want to use that. It's not physical. Okay. So that's why we have to look now at either this defects or others. We have to look at some setup where matter symmetry becomes a physical thing. And once matter symmetry is physical, now Z will carry charge under it. And you can interpret it as an SPT order parameter. But it's, in terms of SPT response functions, this is telling you if I insert flux for the magnetic symmetry, it traps charge. For matter symmetry, if I considerably have a physical definition of matter symmetry, and I'll come to that right now.
So can I just ask, are you saying that in any theory that has an unbroken one-form symmetry that's gapped, I can consider the generator of the one-form symmetry, and then end it? I can always end it on 2 points. And are you saying that whenever it's gapped, you will get this
It has to have long range order for some dressing of the edge. Yeah.
So there exists a dressing of the edge for which it has a. I see. That's just a fact about them.
Yeah, it's a beautiful fact of gapped phase of matter.
Okay, I see.
And it's really the key insight that led to the classification of SPT phases, because that's really the thing one uses.
Right. But then it sounds like you're saying whenever one-form symmetry is unbroken, it's an SPT phase.
Well, okay, gate not just in any system. But the point is, in a gauge symmetry, the Gauss law ties together the magnetic string with matter. I mean, that's kind of what the Gauss law is saying, right? That if I flip the I'm going to have to flip matter. And so if in addition, one can assign physical meaning to a matter symmetry, then the SPT is a consequence.
I see.
But so it's all intertwined with the Gauss law being a type of SPT enforcing thing.
I see. I confess, all the examples I know of one-form symmetries always have a structure like this. So I sort of I'll ask you.
Okay. Yeah.
I forget if I already asked you, but should there be some? Should we think about the one-form symmetry and the zero-form symmetry somehow tied together, because we can only end the strings on zero-form carrying charges? I don't know how to describe that.
Okay, that's the thing. As long as the matter symmetry is unphysical and just gauge, then they're intimately linked by Gauss law. But then it also becomes an empty statement because you can't really decide anything because it's just Gauss law. The point is, that's why you have to go to physical situations where the matter symmetry has a physical meaning. And then it's no longer automatic, and you can discover. I think I'll just discuss the example, it becomes clear.
Okay.
Yeah, sadly stuff is out. Yeah, but
So you
mentioned that you can try to get the charge of the z when it's attached to this line, right? But to do it, you need to surround it by the symmetry surface or whatever. Codimension one object.
Yeah.
And then that codimension one thing will intersect.
Yeah, but it commutes with it. Because
like, can't you put something on the intersection? So is it stable against counterterms?
Yeah, it is.
Is it up? Why is it up this? Or is it up this?
There we use the fact that there's the symmetry generator.
I'm worried that you can trivialize the charge basically by messing with just putting a counterterm in the intersection.
I see what you're saying. This is a concrete setup, so you can convince yourself that it's meaningful. The only subtlety is that gauge stadiums don't have tensor product Hilbert spaces, which prevent you from having a kind of a canonical choice of string operator. But the usual story is in condensator state with tensor product Hilbert space, you have a natural choice of string operator, which is the one that.
I mean, it's perfectly natural if it doesn't intersect with anything. But when there's an intersection, you can naively, at least, you can always say that on the intersection you put a counterterm.
Definitely, in usual scenarios, like abstracting away from gauge for a moment, because you can have your definition of a symmetry, which you require, at least on the lattice. I don't know the field theory speak for the analog of this, but on the lattice you require that your symmetry generator is a tensor product operator. A tensor product meaning there's some notion of unit cells in your lattice, and the symmetry action doesn't map between unit cells. Okay, and once you have that, you kill the ambiguity that you're worried about. Then you can show that if the symmetries globally commute, then you cannot play this game you're thinking of. But yeah. Let me try to put it ahead here. Let's see. Okay, so all this is more suggestive, but the problem, what prevents us from saying this carries physical charge? Well, okay, clearly, I would want to say it carries charge under global matter symmetry, say, right? That's a natural candidate under which Z seems charged, right? Basically, product of poly X on every side, right? That's measuring the parity of matter in your system. And Z anti-commutes with it, but of course, this equals the product of, let me call this G, right, for every vertex, and the Gauss law operator for that vertex. And if you're on periodic boundary conditions, right, let me say periodic boundary conditions, so this was on all matter vertices, I'm checking for the parity, but if you just multiply all the Gauss laws, you can convince yourself these are equal. I don't know if it's clear. If you do the exercise, you can see for every bond, poly X appears twice, poly X appears one. And then, of course, it's 1 because Gauss was 1. So this is just a statement of what we expected. The global matter symmetries gauge. Yeah, can't have charge. But that's in terms of periodic boundary conditions. So one option to find a physical scenario where matter symmetry has a chance to do something physical and protect interesting stuff is, for example, in the presence of a boundary.
Can I get one more question? Magnetic one. There's one form symmetry. Why is the one form symmetry? Why is the symmetry?
I don't think it is, right? I mean, it's not topological.
Oh, that's the usual kind of. There's a very confusing between, I think, transmitter speak and high energy speak there in terms of. I mean, it's a string like. I guess for hydroform, we only want that the non-contractible ones act non-trivial in Hilbert space, I guess. Yeah. So.
It's not that it comes with the Hamiltonian, but it does change if you deform it. So
yes,
it's not the one form symmetry in the usual sense.
Then whatever name you want to have, it plays the same role as it would in the field theory. But okay, I see your point. Then I just don't know what they, this is the thing, and I don't have to say words, but this is the object I'm talking about, and it's a string-like symmetry. I don't know what is a good name for it.
What was the objection that it acts non-trivially?
Yeah.
On local things, because it's in the one form symmetry the way it was originally introduced, it didn't change it before the homology class. It's like this one, of course.
It's a matter of perspective, right? I mean, given it's a symmetry, I can force myself in a part of Hilbert space where this equals 1. And now I've clearly not changed any of the physics I'm going to get. So
if you make made the coefficient in front of this plaquette term infinite, yeah, then you
and commute, so it's effectively infinite. So anyway, it's a bit of a subtlety that, you know, in this symmetry, I could work in the sector where there's 1 on each plaquette, and then you'll be happy, right? And it's not anything I say, so you can always do it. But
in the open space where the plaquette fluctuates, it's not a symmetry.
no, but I'm working with h equals 0. So it's a symmetry, like it's conserved quantity, so I can set it to 1. And now,
well, in particular sector, yes, but in general.
Yeah, okay.
Is it topological in the ground state subspace when h is 0?
You could say it like that, yeah.
Yeah, I mean, I think that's very similar to the field theory. Like in the field theory, I can insert some sort of like Wilson line, and then my topological defects won't be topological if I pass through the Wilson line, right? So I think here, like, if you use the stricture of the ground state, where you don't have any of these m anyons, then it is topological. As long as if you go to excited states, it's not fully topological as long as you don't cross the m. Just like not crossing the Wilson line inserted.
Well, usually
each plaquette is conserved.
I mean, okay, let me just maybe cut this short because this has relevance to what we're talking about. So, you know, yeah, I prefer not to talk about this. One can always fix that sector, and all the physics will be the same. So I'm more interested in finding a scenario where the physical matter symmetry is physical. So let's look at a system with a boundary. Let's consider magnetic symmetry preserving boundary conditions. Right? I have a magnetic symmetry, I mean that string-like thing, and it needs to commute. So one option is, let's look at my lattice again. And let's say it's infinite at all extents, or at least, or maybe, you know, large, yeah, let's say infinite. I want to zoom in on one side. And then it's open, it's a boundary here. So this row will be a boundary row. Okay, and I'll have my Hilbert, or well, my lattice model will look like this. You might ask, why do I choose a rough boundary? It's because I want to preserve magnetic symmetry. And this is a boundary where Wilson lines can leave. If I've chosen a flat boundary, and if I enforce a Gauss law, it turns out it doesn't commute with magnetic symmetry. So I want to, you know, as was usually with SPTs, you better preserve the symmetry when you study the consequence of SPT. So there's a slightly more complicated story you can do for smooth boundaries. Let me choose this simple case to discuss.
So will the result you will be presenting later depend on the choice of the boundary?
No, it depends on choosing a symmetric boundary. And this is just a nice system.
If it's not symmetric, then what?
Yeah, then okay, then it's similar to the topic of h equals non-zero, and so that was one of the effects of non-zero fluctuations. Okay, so why is this an interesting scenario? Now, the global matter operator, if I try to play this game again, right, it no longer equals the product of Gauss law terms. Right? Or to say differently, the product of Gauss law terms, if I do this game, right? So the Gauss law term is this 5-body thing, right? If I multiply it on all sides, you see that in almost all bonds, the bond variables square out, except the boundary row. So this equals, and of course this equals 1. This equals the parity times the links on the boundary, and there I have a sigma x, right? Just to remind you, Gauss law has sigma x on the links, right? Or to rewrite it differently, this equals sigma x on the boundary. What's the conclusion? Global matter parity is physical because of boundaries. That's what this equation says. It's no longer trivially equal to identity. If we're wondering about the physical interpretations, it's telling me the symmetry is saying that the electric flux through my system cannot change. Because this thing is measuring electric flux, and it's basically saying that the amount of charge in my system cannot change. It's a physical condition. If I allow it to kind of hop charge off my system, I can violate the symmetry, and indeed every symmetry definition can possibly be violated. Otherwise it would be gauge. Okay, good. Why is this interesting? Now we have a system where matter parity is an actual physical symmetry. So now it looks back at this. Now it's generally an SPT order parameter in the sense of the string of one of the symmetries, in this case magnetic symmetry, has long-range order, but the endpoint carries non-trivial charge under another symmetry. And indeed, if I have a boundary, right? Now we have to see it's physical. Yeah, this singles. I have to say it. In the presence of a boundary, I can define a local charge operator. Sigma z x, and this 2-by operator. Notice local. It's gauge invariant coming to the Gauss law term, right? But it's charged under matter symmetry. And again, physically it makes sense. It's like putting in a single charge and the electric flux where the boundary is changed, and that's what you're measuring.
Sigma z z.
Did I? Oh, thank you. Correct. Okay. So now we have two physical symmetries, and I would argue that the bulk is a non-trivial FPT. With respect to it, what does it mean observationally? For example, it means that the edge must have an edge moment. Okay. So how to see that? How to directly derive this? So consequence. The edge has a mixed zero form and one form anomaly, where zero form refers to matter, one form refers to magnetic symmetries. But on the lattice, we can be very concrete. We can just see it. So to see it, actually, very simple derivation. Okay. So let's again consider the lattice, which is the boundary length here. And let's use the bulk fact we already derived. In the bulk, we know that this has long-range order, right? So z, sigma z, sigma z, sigma z. Z has long-range order. Right? So what I mean is, arbitrarily, no matter how far away you put these guys, has non-zero. And now let's use a magnetic symmetry to push this Wilson line into the boundary. This equals so this will move on to here, so sigma z z, sigma z z. If you just look like the Wilson line is running off the system, coming back here, and I interpret that way. So you see what I mean? I can just move, right? I use the local plaquette conditions to move this Wilson line off. So that's equal. But why is this interesting? Now it's a 2-point function. So now I have long-range order and 2-point function. And this object is exactly the thing I was discussing here. It's a local, invariant charge object.
So sorry, is there a plaquette term for the
Yes, yeah, exactly. Yeah, there's a plaquette term as well. Because you can add it and conserve the symmetry, so it's a, yeah.
So there's like a
yeah,
sigma z,
exactly.
sigma z, sigma z.
Exactly.
Triple.
Yeah. Yeah, sigma z. Any fine-tuning is actually not important, but this is a term where you can solve things in some limit exactly. But the main point is, you should allow symmetric boundary perturbations. This is one, and indeed then you can use it to push it. So now we have, we can have, now we have, okay, basically this is spontaneous. Okay, this is also fun. It tells you that the Higgs stays in some sense spontaneous symmetry breaking, but just at the edge. So spontaneous symmetry breaking of the matter symmetry, which indeed acts like electric flux on the boundary, which is spontaneously broken here. Why is this anomalous? Just like the superfluid case, which is of course much richer and more interesting, superfluids have emergent anomalies for the global symmetry and the winding number. You can think of discrete symmetry breaking as emergent anomalies in a more budget way, where the symmetry is on the one hand a spontaneously broken one, and the other generators like the order parameter in a way is there kind of a, it's more like a side comment. So that's these statements are consistent. But the main point observationally, there's some edge mode, there's a degeneracy there. So if you solve the system with boundaries, with the Gauss law, etc., that's defined as you really do find degeneracy. And this argument is very general and works along the whole axis. So indeed, if we did matrix on the system, you find twofold degenerate boundary. I think I'm kind of running out of time. Well, okay, still 10 minutes, I guess. Okay. So far, I focused on the case where exact magnetic symmetry, right? And we were able to derive the net law. And moreover, I think, at least this is an observational, like I try to do this perhaps on observational level, that it has the consequence that it would have if it was a non-trivial SPT phase. But let me focus on what happens if H is non-zero. We tune away. We tune away from the axis. Will things immediately go away? And actually, no. One way to simply convince yourself, well, symmetry breaking with Z2 symmetry, that's robust, right? You can't immediately destroy symmetry breaking as long as you preserve the symmetry at Hamiltonian level. But in this model, you can actually solve also, if you go to infinity, turns out this line is exactly solvable, and you can actually prove that that until H is 1, okay, this is not drawing scale now, there's a Ising critical point at the boundary. And this whole line, you can prove you have Z2 symmetry breaking. Okay? If I had more time, I could have shown you how to derive that. Actually, very simple. Basically, in this infinite limit, you can show that the effective theory is only at the boundary, like the bulk is kind of frozen out. And you can solve for the boundary, which is a 1D system, and you can map it to a quantumizing model. And we know what a quantumizing model is in transition. Okay, so actually, so far what have we derived? There's symmetry breaking at the edge here. There's symmetry breaking at the edge here. And those are the limits we can kind of do by exactly solving or doing general arguments. And then the question is what happens away. And then we added network simulations. And what we find is, okay, here was a cut, right, from, okay, my lattice broke from infinity to finite. So let me just kind of look something like this. So we have a whole line of 1 plus 1D Ising CFT that we see in the numerics at the boundary. And then in this whole region, we see a two-fold degenerate edge. We can't quite resolve what happens here. It will be interesting to do some large system study where precisely it ends. But the main point is, it is stable. And you can argue indeed, right? If you have Z2 symmetry breaking, it's a gap phase, any perturbation which respects the Ising symmetry can't immediately be restored. You're going to have to go through a transition. Yeah?
Along the transition line, the EM exchange symmetry probably forces you to have critical Ising on the boundary?
No, it's actually not. It actually works. Here it wasn't clear because of my warped scale. But if you do it in if you draw it to scale in the paper, it actually looks something like this. So it's not at the EM duality. Maybe think about the boundary actually breaks the EM duality, so there's no need for it to play a special role.
But there's a dual edge mode.
Oh yeah, you can play the whole story if you want to think of the electric line symmetries, but yeah, stuff that's true.
But it's different boundary conditions.
Yeah, smooth one.
There's no boundary conditions which will give you edge modes in both the confined and Higgs fields.
I don't think so.
Did you do boundary numerics for the multi-critical point part of the phase diagram?
What was the question?
Did you do the boundary? Did you extend your numerics for the boundary to the multi-critical point?
Yeah, we did there as well. Yeah, but it's as you can imagine, the bulk is very critical, and for our purposes, we didn't need that big system size to see the boundary criticality, and I don't think we're not big enough to flow to the IR of whatever this theory is. So yeah, we need bigger system size to figure out what precisely is happening. There are things merging is coincidental. For this particular choice, the model does seem to roughly end there, but that might be circumstantial.
Ruben, I think you mentioned it just to confirm. I guess here the key point, one of the key points is that the Gauss law has a consequence of giving rise to this matter symmetry.
There's two separate things. So the Gauss law enforces that the magnetic symmetry has something that carries a matter field in some sense. If in addition you have scenarios with physical meaning to matter symmetry.
But from this example, it seems like as long as you have Gauss law, then there is some kind of physical meaning.
Oh, I see what you're saying. Yeah, well, you know, if you look at this boundary condition, I would say so. Yeah. If you look at the measurement, I mean, at the same time, it's a bit subtle to study Gauss theory with boundaries. The main point is everything I said carries through for this bulk defect thing. In fact, there's a point worth making that if you don't like less Gauss theories with boundaries, which admittedly is a bit of a, you know, subtle game to play, you can do all of this in the bulk, right? So you can have, you can study this lattice model, and now again, see periodic boundary conditions or infinite extension, then say along these bounds, you say there's no tunneling. What that means is the lattice model, you set j equal to 0 on these bounds. Okay? So if you modify the Hamiltonian like that, the hopping is not present in this Hamiltonian. Everything carries through. Now there's a physical matter symmetry again, which is the thing that carries charge under z, sigma z, z. Which is now, again, it's similar to this U1 discussion before the break. It's like I take a particle from one end, deposit in the other. And but because charge cannot dynamically move, this is actually a charged object under conserved symmetry. And you can show that this no tunneling defect has Z2 symmetry breaking. And everything kind of carries over. And if you then take the special limit of this phase going from the fixed point limit of the Higgs phase, it looks like a boundary theory. And so even for this, again, we get that there will be some kind of region where there's an anomaly on the defect as you tune the Kretkin-Schenker phase diagram. And then there's a critical strength of magnetic field fluctuations where there's a Ising criticality on this boundary. And then you have a unique state. So again, like all the SPT results can also apply to this bulk defect if you want to stay from the edge. Okay, I think maybe then the last thing I just want to, clearly I'm not going to be able to talk about the U1 case, which I guess, I kind of schematically did. Maybe one point worth making is that this also gives, the lattice case also gives a nice situation where you can exactly solve this conceptually simpler case. If you remember early on, it's conceptually simplest case where you have two matter fields, right? So indeed, we also went through that. So, right, so you can imagine you have two matter fields. Then the Gauss law would look something like, let's say, let's call them A and B. Right, so the Gauss law would be now matter for the A degree freedom and matter for the B degree freedom that both live on the lattices. Right, again, the Gauss law is like this. Basically, this is the Z2 Gauss theory you would write down for two matter fields. And then a Hamiltonian could be again something like chemical potential for the A field, chemical potential for the B field, the little flux penalizing term. And now we can have hopping for both of the fields. So ZA, sigma Z, ZA, which are standard, we just write it schematically. I hope it's clear. Again, these three-body terms on the bonds. Right? So now I have two Higgs fields that are independently hopping. And suppose I don't allow a term that mixes them. Right? So now this has a physical bulk symmetry. For those of you not happy with kind of the previous symmetry kind of living at a lower dimensional region, now it's a physical bulk symmetry, which is the product of X, A, and all vertices, right? Which even in the bulk is not Gauss symmetry. Right? Then you can now meaningfully say that the large JA regime is one Higgs phase, the large JB regime is the other Higgs phase, and you can rigorously show that they're generally distinct bulk SPT phases. Now you don't even need to look at defects or edges or nothing. And then in this case, it turns out you can exactly solve the phase diagram. So now both axes are Higgs tuning, so I preserve the Higgs symmetry throughout for simplicity. And now I have the Higgs A, Higgs A, Higgs B, deconfined. And it turns out the exact solution gives distribution, quote unquote. More precisely, you can exactly map it to previously studied models. And then here there's Z2 symmetry breaking. So basically, there's an exact version of the schematic phase diagram I had before. And now it turns out this one actually has a continuous SPT transition between the two. For detail, I'll refer you to the paper or chat later, in the time. So it's kind of, I just want to mention this, because there we can exactly confirm there's no way of connecting them. And we saw indeed that there's an SPT transition between these two different Higgs phases. And we actually really need the SPT concepts. It's going to look very weird to try to describe it differently. Wouldn't be as nice.
So what's the CFT? What's this?
I guess there's a paper now, but I guess it's morally it's this. It's gauge O2. Morally, because this fine-tuned model is actually Ising times Ising gauge C2, but we know that generically will flow to this if we add some generic perturbation. So
how does it reproduce the anomaly?
What?
Reduce anomaly at that point.
Yeah, let's go. Yeah, there should be anomaly, SPT anomaly there, and then now if you also imagine adding a third axis where you allow fluctuations, then strictly speaking, the Higgs phases are no longer well-defined SPT phases because we've broken on the symmetries, but this critical spoke will stick out. You can't immediately gap it out. That's the whole point. Like I'm talking about things are stable to physically breaking the high form symmetry. And so this three-dimensional phase diagram, there's some gap path eventually, but there's this critical spoke sticking out. We kind of emphasize, even if you don't have exact high form symmetry, all these considerations can be important.
So if I, instead of slightly breaking the higher form symmetry, I slightly break the Gauss law by imposing it energetically, what happens?
That's fine, yeah, stable. Yeah.
Done.
Yeah, it's all stable. Well, so, okay, let's skip U1 stuff. So, done. So then just to maybe just zoom out for a second. So I try to convey to you this 2-hour frame a bit of the idea of saying that Higgs phases are SPT phases. And admittedly, if you have one Higgs field, you have to play these funny games, looking at boundaries, looking at defects. But at the same time, if that looks too fine-tuned, it's exactly the stuff we do with superconductors. We put a little insulating region, we look at Josephson effects. And sadly, the one thing I'm sad I didn't have time to mention is supercurrents are quite fun because then it's more like an interface between the Higgs phase and the Coulomb vacuum at the edge of the superconductor, which is not in a trivial phase, but it's a Coulomb phase. And the whole fun story there about supercurrents being topological Talos problem due to the SPT, and what being gapped out by the vacuum. I think there's a fun different directions to explore. So on the C2 case, we did the lattice case theory studies. And for U1, we defined the problem on a lattice as well, and we expect there to be edge modes and defect transitions, but we haven't been able to do numerics, so it'll be a very interesting direction to explore into. One thing I'm going to connect it to David's comment earlier on, because I think it's, so the stability here implies that a Josephson effect is stable to including monopoles in our universe until they critical. So apparently, if we suddenly have monopoles going around, there will be a threshold value below which we have Josephson effect, and suddenly our Josephson junction will go critical, and then beyond it we lose it. So I think the SPT perspective helps to get insight into this. So, and some other questions would be like what happens with kind of temperature, and what more exotic superconductors to consider. And lastly, I think having connected superconductors or Higgs phase to SPTs, it also allows you to export back insights to the SPT side. Right? For example, all these games of playing with defects should also work for general SPTs. So, and indeed, we try to argue in our paper that there's a generalized bulk defect correspondence, not just bulk boundary correspondence. Okay, let me shut up now. Thank you for your time.
Any questions?
Yeah, I just want to make sure I understand something about the case where you do have to play games with the boundary.
Mm-hmm.
So there, if you had added other symmetry-preserving terms on your boundary, presumably the red part of the phase diagram would have moved, right?
Exactly.
Okay.
Precise shape is not universal. The existence is universal. And precisely, you can prove there's an open region containing the y-axis that has this long.
So given the bulk, you can't really assign these things to that.
And see, that's why I would say this region has an exact bulk SPT which implies the anomalous edge or a defect, etc. And then anomaly is parametrically stable. But I personally wouldn't say that bulk SPT here for the reason you just mentioned.
Does there exist a theory with an unbroken one-form symmetry that is not an SPT phase?
Graph gauge theories?
Any model.
Oh yeah.
Which one?
Product state.
Okay, maybe not that. Maybe an interesting one.
Okay.
Curie and Mills theory. It's interesting, but
pure Yang-Mills theory, because it's just that I always like the simplest models that have unbroken one-form symmetries, and it seems that very general arguments resulted in this SPT phase. So I was wondering,
if you have the physical matters, but then if you declare you're not interested in the physical matters, or you don't want to look. But the Higgs field, you have to play these games with it.
Yeah, but it almost like this is almost the most generic way to have a system with only one one-form symmetry, right? That's basically what you wrote down.
Well, in the Gauge theory, but as soon as I give up on the Gauss law, I no longer.
Yeah, but I always thought you can almost always write them as gauge theories if you do enough values and so on. Like it didn't really seem like that was.
Yeah, but then if you take a trivial system and you add as a gauge theory, you might not be able to find. Well, if you then introduce no Thomas defects, etc., you would recover the same thing.
Yeah.
But then, yeah, it'd be interesting then to like map that back to the original on-gauge language, and then you did something that implied the edge mode, but I don't know what understanding the original language.
I see.
That might be fun.
Okay.
That game to play.
So, did you say there is an example of a theory with a one-form symmetry?
Oh, just forget about the gauge theory stuff. Yeah, just the product state has like two symmetries.
Yeah. Okay.
I understand it's not
anything with dynamics, maybe. Yeah, maybe that's what I was saying. Anything with dynamics that has a.
I can perturb the product state as data. But
Okay. Yeah, I'm not sure. I feel like I think you could run these arguments for the pure Yang-Mills theory, probably.
so probably find it as a trivial SPT.
Yeah, trivial SPT, you think?
Well, anything as some random system will be a trivial.
Yang-Mills, if you take it like 2 pi theta by 2 pi.
No, theta equals 0. I want the trivial.
Yeah, I'm not so sure. We have to think about this. I'm not so sure actually.
Good luck.
So if you try running this the same thoughts with 1 plus 1 d2 gauge theory, it's kind of like an Ising model, but the domain models are dynamical matter.
Yeah.
I feel like all the arguments will carry over.
Yeah. Well, except the stability. So we studied the one.
Yeah, of course. Except for the stability.
I agree. So we also discussed 1 plus 1 d.
I see. So this would be purely zero form, no higher form.
Yeah. That's actually how it started. We first studied some 1D spin chain, we gauge some stuff, and it's an SPT, and then
I see.
We try to see if it breaks down high dimension.
So why does that? When I see this flat model through like the Z2 1 plus 1 d gauge theory, I kind of think it's like the transversal Ising model, and I would think like the Higgs phase is kind of like a paramagnet, and then like the D confined phase is like my normal.
Yeah, it's a good question. Sorry.
Yeah, I'm assuming it would be incorrect to say a trivial paramagnet is a non-trivial SPT, but I actually don't know why.
It's a really good question. So we try to. It's a good point. Try to carefully just in the paper is that when you go through like say even the 1D lattice model as gauge theory, and you have Higgs phase, and you say you consider this a paramagnet. What you've secretly done is the SPT entangled, and it's a fact that SPTs are short-range entangled, and you can describe trivial phases after doing a basis transformation. But that basis transformation turns out cannot be done symmetrically. So if you care about magnetic symmetry, you cannot describe the Higgs phase as a paramagnet in a continuous, like you can't disentangle it continuously. Maybe we can chat more later, but that's a claim that if you do it carefully with considerations of symmetry, it turns out it's an SPT, not a product state.
Okay, I'll
yeah, we can chat. Happy to chat.
Sorry. So are you saying that this is an SPT protected by 0 form Z2 and 1 form Z2?
Right. That was
so is it in the same phase as the cluster state on a square lattice? Or?
Yeah, you can think of it like that. Yeah, I would say so. Yeah. Okay, so
Let's
thank you.
Let's have lunch. Well, thanks.